In this lecture, we will explore a popular supervised data mining technique called K-nearest neighbors, or KNN. You would notice that the names of several data mining techniques start with the letter K, which refers to a number that can be any integer. Therefore, KNN means a certain number of nearest neighbors. As the name suggests, it is a technique that makes prediction based on a number of nearest neighbors. KNN belongs to a category of data mining techniques called memory-based reasoning. What is memory-based reasoning, or MBR? Let me give you an example. You're on an airplane and started to have a conversation with the nice man sitting next to you. A few sentences into the conversation, you realize that the person is from Australia. So how do you know that person is from Australia? Well, is it because of the person's Australian accent that gave it away? How do you know that is an Australian accent, not a British accent? Maybe you have watched the movie Crocodile Dundee way too many times. Or maybe you know someone who is originally from Australia and speaks in exactly the same way. Well, what I just described is memory-based reasoning, being done unconsciously by human, and of course in a slow motion, compared to how fast the computers can do it. The premise of memory-based reasoning is that we tend to guide our decisions using the memories of similar situations we experienced in the past. We do this hundreds of even thousands of times each day, and we don't even realize that. The same idea can be applied to a machine learning or artificial intelligence technique called K-nearest neighbors, which allows computers to make decisions based on past experience or cases. KNN is a data-driven technique, not a model-driven technique, such as regression analysis. This makes KNN highly attractive for many applications where clear patterns in data cannot be easily found using traditional statistics methods. Furthermore, it makes no assumptions about the data, such as normal distribution requirements. However, the downside of a data-driven technique is that it often does not provide you with a model that explains the decision-making process, making interpreting the findings more difficult. But keep in mind that data mining is a predictive modeling process. Interpreting the model is secondary to making predictions. Data-driven techniques such as KNN can also benefit from large data sets. The more cases or past memory that we can feed the computer, the more accurate the predictions are. KNN supports supervised data mining, meaning that it can be used for both classification and prediction problems. Although in real life, KNN is often used more commonly for classification problems, where the target variables are categorical than prediction problems. Since it is a supervised data mining technique, data partitioning, model complexity optimization, and performance evaluation are all important steps in the process. In this lecture, we will focus on three key topics related to KNN. First, how to identify the nearest neighbors. This involves the topic of similarity measure that we discussed in previous lectures. Second, how to optimize the complexity of the model. Or in other words, which number should the K be? Should we consider 1 nearest neighbors, or 5 or 20 nearest neighbors? And third, how do we make the prediction based on the nearest neighbors? How can the information from the neighbors be combined to produce a single prediction? We will tackle each of these topics in this lecture. There are many practical applications for the KNN technique, most of which involve classification, but there are also prediction applications. Common applications that use KNN include consumer credit rating assessment, loan application evaluation, fraud detection, medical diagnosis, and even music recommendation systems. KNN is also a technique for digitizing expert opinions. Therefore, it is often used in building expert systems as well. For example, a credit card company may evaluate the creditworthiness of a new credit card applicant based on what is known about past applicants. The past applicants that share similar financial and social demographic characteristics are considered near neighbors of the new applicant. Decisions about the credit card application can be made based on how similar applicants behaved in the past. In the medical field, the symptoms of a new patient can be compared to the symptoms of past patients in the database to identify nearest neighbor cases. This will help doctors to reach a diagnosis faster and know what to expect if the symptoms develop. Another example that many of you can relate to is the music recommendation system, such as Pandora, that use the KNN technique to identify songs that are similar to each other. Each song is rated by music experts on a wide range of qualities, such as acid rock qualities, accordion playing, acoustic electric sonority, acoustic synthetic sonority, and etc. Songs that have similar scores are considered the nearest neighbors and recommended to listeners when they like the other songs. These data-driven techniques can sometimes lead to surprising results that humans could not comprehend. For example, who knows that a Beatles song would be similar to a Bee Gees song and liked by the same listeners? Unexpected findings do not mean ineffective findings. It is important to keep an open mind in data mining, especially with data-driven techniques such as KNN. As you can see from all these applications of KNN, similarity measure is at the heart of the problem. Now let's talk about how nearest neighbors are identified in KNN. Let's look at an example. Suppose a bank has a data set about 10 current credit card customers, and the variables are age, income, and whether they paid their credit card debt on time or are delinquent on their payments. If we plot the 10 observations in a scatter plot, it should look something like the one on this slide. The x-axis is the income values in thousands of dollars, and the y-axis represents the age in years, and the color of the dots represents the payment status. Blue means paid on time, and the red means delinquent. Now we have a new credit card applicant. The applicant has an income of $64,000 a year and is of the age of 36. We can draw the new applicant on our diagram using a green triangle. Who are the nearest neighbors of the new applicant? Well, if we draw a circle around the new applicant, we can easily find that the 3 current customers within the circle are the closest neighbors of the new applicant. They are close neighbors because they are physically closest to the new applicant based on income and age. As you can see in this example, close neighbors are selected based on their distance to the case. If we use the 3 neighbors within the circle, how can the bank decide whether the new credit card application should be approved or denied? One simple way is to find out the probability of the new customer to be delinquent on payments based on the behaviors of the current customers that are like the new customer. If you look at the 3 nearest neighbors, 2 paid on time and 1 is delinquent. That suggests that the new customer has a 1 in 3 or 33.3% chance of being delinquent. And similarly, a 2 in 3 or 66.7% chance of paying on time. If the bank uses the default cutoff rate of 0.5 for binary class problems as the cutoff rate, then the new customer has a higher chance of paying on time than being delinquent, therefore should be approved for the credit card. However, as we discussed before, the cutoff rate used in the problem should depend on the business context of the problem. If you look at all 10 cases, 3 out of the 10 customers are delinquent on payments, and that suggests an overall probability of 0.3 probability of being delinquent. The new customer has a 33.3% chance of being delinquent, which makes him or her less desirable as a credit card customer. This example shows us a few important concepts. First, similarity or distance measures are used to identify nearest neighbors in KNN. Second, using different numbers for k will likely generate different results, or probabilities of the new case belonging to the target class. Instead of 3 nearest neighbors, if the bank chooses to evaluate 5 nearest neighbors, then the probability of the new customer being delinquent would have changed. And finally, a sliding cutoff value is probably more meaningful than the default cutoff value of 0.5 in many cases, and the domain experts need to be consulted when making these decisions. In this example, since we only have 10 observations and 2 predictor variables, it is intuitive to identify the nearest neighbors on the scatter plot. What if we have tens of thousands of observations and dozens of predictor variables? Well, then the visual inspection would be impossible. Therefore, we need a formal mathematical approach to help us identify nearest neighbors. Let's first talk about similarity and distance measures. Technically, any distance measure can be applied to the KNN technique, but the most popular distance measure used in KNN is the Euclidean distance that we discussed before. Euclidean distance can be applied to multi-dimensional spaces, making it very versatile to identify nearest neighbors in a wide range of applications. Since Euclidean distance only works with numeric variables, categorical variables must be transformed into dummy variables or category scores in order to make it work. In addition, since Euclidean distance measures are influenced by the measurement scales used for the variables, standardization or normalization are needed before the computation of distance measures. Since we have discussed the Euclidean distance measures in great detail in the previous lecture, I am not going to repeat it here. If you want, please refer to the similarity measure lecture for more details.